Hello, my name is Bradley Alicea. I'm from the Orthogonal Research and Education Lab, OpenWorm Foundation, and the University of Illinois at Urbana-Champaign. And today I'm going to talk about allostasis machines as continuous cognitive modeling. So, allostasis machines can be defined as a system where the output characterizes a cognitive architecture under allostatic regulation, subject to environmental perturbations. And I have a sketch of what an allostasis machine looks like, its inputs, its outputs, and the perturbations acting on the output trajectory. So one point about allostasis machines is that initial outputs are based on an equilibrium system of information processing. So the perturbations are countered by some equilibrium-seeking force. And that's not defined in the model, but that's the way it's being modeled mathematically. Number two is that the output trajectory is impacted by environmental perturbations. So those red arrows in the diagram I showed before are environmental perturbations, and those can be things in the external environment that impact performance. Number three is that trajectories either recover from a perturbation or tend towards a new stable state. Failure to do so is a no-matched response and produces instability. So we'll see examples of this in the talk. So one example of an allostasis machine is by looking at feedforward behavioral states, which are the output, that can be perturbed by environmental factors. And in this case, we have sensory information serving in as an input to an internal model, which can be specified in different ways. And then the output is the initial condition, which is the first step that form this continuous trajectory. Perturbations are the red arrows and act upon this trajectory and force it either to become unstable or to go to a new state. And then the model, in response to those perturbations, recovers to a certain extent. It either recovers to the initial condition or recovers to an irregulated state. In short, the sensory information is regulated and is processed by the internal model. Then the trajectory recovers to a new stable state and resets the internal model input. And this is a feedforward process when an output state trajectory recovers. It either recovers to the initial condition or it exhibits something called hysteresis. And hysteresis can be defined as when the output of the system lags the intervention. So a perturbation occurs, there's a deformation of this trajectory, and then it either recovers to its original state before the perturbation or it recovers to a new state. And that can be any sort of hysteretic state. It can either be an unstable state or it can become an irregulated state. If we consider a feedforward behavioral response, we can also see this as a feedback between the trajectory states and the internal model. This is an example of a trajectory being generated by this spinning top. This is something called an intermittent wobble perturbation, something we expect to see with our allostasis machines in terms of the trajectory. We have a number of perturbations, as you can see with the spinning top, and those perturbations and subsequent recovery represent this wobble. This trajectory isn't really based on the spinning top, but you see how the perturbations act to push the system away, and then in the case of the spinning top, the inertial force brings it back to the initial state, or at least tries to recover that initial state. And so on the lower right-hand side of the slide, you see a dynamical trajectory produced by the spinning top. So you see that it produces dynamics at different temporal scales. So if we look at the different components of a hysteretic response, we see that there are five. The first is the baseline condition, and this is analogous to the initial condition that we talked about in the first slide, known as component A. This baseline is then changed by a perturbation C, so there's a strength of the perturbation which forces the trajectory downward, and that is characterized by magnitude B. So the perturbation is the external forcing, and the magnitude is the response of the trajectory. Then D is the recovery, so the recovery can be complete or it can be with some degree hysteresis. So complete recovery would be a hysteresis of 0. A hysteretic response could be a positive recovery or a negative recovery. And then the recovered state is E, and again, this can either go back to the initial condition or it can go to a shifted state, and that can either be a stable state or an instability. So that was the machines part of allostasis machines. Now we'll talk about the allostasis part of allostasis machines. So allostasis is the brain's ability to anticipate adverse events and shifts in environmental conditions based on energetics. So this is a theory that's been cited in a number of papers from Sinesh, Katsumi et al., Sterling, and Billman. And so this is an emerging area of neuroscience where they're looking at the energetics of the brain, this generalized response. It underlies the cognition. The first component of this is an energy gradient. This energy gradient operates on a domain general matter, and it operates on the sort of metabolic demands of the brain, the system's level demands of cognition. So it regulates cognitive dynamics in that way. It also summarizes the complexity of multitude causal relationships, which include both normally and exponentially distributed events. Allostasis is a systems level response. Particularly, it's a feedback response to distributions of environmental stimuli and intervals of discrete events. So remember, we said our internal model is a generic box, and in that box we can put anything. The first example I'm going to give is that of an oscillator, a simple oscillator that oscillates at a normal frequency. And so we can see that we can take that output that comes from that oscillator, and we can isolate stochastic oscillations, and we can look at that as a distribution of events as the output. And then we can look at the mean activity. So the mean activity is the thing that forms a trajectory. The trajectory shifts when the mean activity shifts. Then the oscillations change or become abnormal or shift their distribution, and then the mean activity shifts as well. We have perturbation and feedback, so we have constant information coming into the system, both perturbationally and in terms of feedback. And so this is, again, leads to this distribution, but it also gives us this gauge for hysteresis and what might constitute a hysteretic response. So if the oscillator aligns with perturbations, there's no hysteresis, and this is what we call a matched response. However, if the oscillator is out of phase with perturbations, hysteresis can move the system to an unstable or a newly stable state. So now we can look at the effects of feed-forward and feedback mechanisms on hysteresis. So in the top example, we have the feed-forward mean in red and the hysteretic response in black. So we have the mean in red here, which is close to 0.0, and then there's a perturbation, and then there's a recovery, which is negative, and you see the black line there, which is the shifted feed-forward response. The second example is a full recovery, no hysteresis, and so we have a black line here that is unchanging. It's pretty close to 0, and it basically results in the same state, maintains its state. The second example is feed-forward, and this feed-forward signal is in black, and then the shift is in red in this case. So in this case, we have a positive shift from the black line up to the red line, and so this feedback signal is actually giving us the inverse of the effect of the hysteresis, and that should give us some more information about how to recover the initial state. We can make the internal model more sophisticated. So in this case, we have an oscillator, and that produces an output. And there's a feedback, like we showed in the second example in the last slide. That oscillator produces an output, which is the trajectory. Then that trajectory provides a feedback to a memory with capacity. So a number of events can be stored in that memory, and it can inform the oscillator in terms of how it produces subsequent outputs. So this is one mechanism for how you can recover the initial state, how when you knock the system out of equilibrium, it can find its way back to an equilibrium state. So in keeping with our idea of summary statistics, we might want to focus on inter-arrival times, or the time between perturbations. And so if we focus on the inter-arrival time, we end up with this distinction between Markovian systems and non-Markovian systems. So the first example is of a Markovian system. And in Markovian systems, the inter-arrival time between perturbations is exponentially distributed. And we can characterize this with an internal model. So we can characterize this with something we've previously called Gibsonian information, which is a Markovian information processing system. So briefly, we have environmental signals that have a Poisson distribution. They're encoded in this series of inter-arrival times. And those inter-arrival times are then decoded as some information that acts as an output. So the entire internal model is basically the system of processing these Poisson distributed events and then producing an output. The second is a non-Markovian system. So this is where the inter-arrival time between perturbations is not exponentially distributed. And so this is something that from a paper in Chaos, this example here. So you have your time intervals where there's no exponential distribution. The distribution between events is normally distributed. So you have this distinction between a Poisson process, which is exponentially distributed, and a deterministic process, which is uniformly distributed. In the exponential case, there's a random distribution of perturbations, and those events occur with no discernible pattern. And this can lead to dynamics such as cognitive avalanches and other types of nonlinear responses. In the uniform case, you have a predictable distribution of perturbation events in time. And if you include a memory, that memory of those events, because they're uniform and there's some expectation, it can allow for patterns to be matched and prediction to occur. So this is an example of a cognitive avalanche. This is where we have our oscillator input at the top. It's stochastic output. And at the right, we have an avalanche discharge from these oscillator outputs. So the avalanche discharge requires this sort of memory, this sort of compilation of events in memory, and then a collective response. So it's almost like an average of those events and then a discharge. And so what you can get from that is you can turn these oscillator outputs into these avalanches, which is basically 1 over F noise, and it allows you to have these responses that are distinct from oscillator outputs. The second set of concepts we'll talk about, and talked about in the paper, is this concept of ergodicity and non-ergodicity. So ergodicity is a state where the system is well matched to its environment. And this is, thought of in cybernetics language as homeomorphic. Non-ergodicity, by contrast, is a state where the system is ill-matched, and it results in a drift to a new or unstable state. Then there's this concept of ergodic homeomorphism, which is important for the paper, and especially in one of the figures that I'm going to go over next, which is where you have a perfectly matched system output and perturbation. So in the example at the right, this is the footprints of this person walking down the beach that remain parallel to the tide. And so this is where the footprints are matched to the tide line, and everything is pretty much even. And so when we think back to those previous examples, what we're trying to achieve is this ergodic homeomorphism. So in the paper, we talk about quantifying perturbation. You have these different components of perturbation, and it comes out to this mathematical formula of perturbation versus recovery. The perturbation component is the how much the system is deformed by the perturbation, and the recovery is how much the internal model and its output can recover from that perturbation. And this is 1 hertz of a trajectory. So the perturbation and recovery is a 1 hertz frame. So we have 4 conditions that we can have. We have ergodicity, we have positive hysteresis and negative hysteresis. Positive hysteresis being overshoot of the original trajectory, and negative hysteresis is a failure to match the original trajectory. So that negative hysteresis is that negative component. Positive hysteresis is a positive component. And then there's, of course, the sufficient response to perturbation, which is, of course, maintaining ergodicity or that ergodic homeomorphism. So this is from one of the figures in the paper where we have an 8 hertz segment, and of course they're not evenly, not of even length. We have 2 components per hertz. We have the perturbation and the recovery, and we have these distributed. The perturbation is in gray, the response is in white, and you see that they have different time lengths. And of course, then we have our ergodic and non-ergodic components, gray and white. And so we can segment this 8 hertz segment into these ergodic and non-ergodic components, basically where the response is appropriate, which are the ergodic segments, and the non-ergodic segments are where we exhibit some positive or negative hysteresis. And then we can look at the spectral power, and in this example, we just have these different components distributed along the power spectrum, and we can actually analyze that to look at the response of different sized perturbations. So this is an example from a continuous visual attention task. This task asks the person to track the star field with perturbation. So you have the star field moving, you have perturbations, which are these bright stripes, and you can have someone sit on a treadmill and look towards this pattern and be perturbed with these stripes interspersed in the star field. So the person's tracking the star field, they're disrupted by the stripes, And in a postural sway paradigm, you can actually look at how the visual system and postural stability entrain with star fields and then are perturbed with these perturbations. This is a figure from a typical postural stability experiment, but this is going beyond that, thinking about the role of perturbations in this type of sensory motor behavior. This is an example of what the internal model will look like. You have an expected magnitude of perturbations, where basically that power spectrum is the memory. You have an oscillator producing an output. This could be additive perturbative noise, so it brings in those different magnitude perturbations, information about that into the oscillator. And then you can ask the question of the output, how robust is the behavioral output to perturbations of different sizes? And so you can see a postural sway example at the top. And of course, postural sway, even when it's normally entrained, it has this sort of stochastic set of stochastic components in it. So we can actually think that the response to perturbation might be more a nonlinear effect than this. Finally, we can add allostasis machines into other types of artificial agentive models, such as metabrains. So we've introduced this concept of metabrains, where you have these layered representational structures where you have different levels of representation or different orders of time that are represented in them. And so we can actually look at different orders of feedback in these metabrains and produce different outputs, and then integrate them in different ways to provide information both to the internal model and to recovery from perturbations. So in this case, different types of representation in the internal model produces trajectories smoothed at different scales. So there's some limitations of this model. For one, we have a potentially high computational complexity. When these are implemented in silicon or in some sort of intervention, there's a high computational complexity to maintaining this model of allostasis. And so there's this naturalistic aspect, which is that the resolution of the model is contingent upon the sampling rate. So the sampling rate, as we saw, varied, and so it depends on the sampling rate. Also, if you model this in silico, it runs in polynomial time, particularly for multimodal contexts when you're adding in different sensory streams, not just vision, but different types of proprioception and audition as well. The second limitation are limited processing capabilities. So we're trying to summarize entire cognitive functions with single parameters. We're also making assumptions about predictive processing and other mechanisms that are maybe very consilient with this, but also make a bunch of assumptions about human cognition. So thanks for your attention.